Okay, so hi everyone. Welcome to the Mitaketran PD reading seminar. Today we have Takuya Sato, who is currently a PhD student at University of Tokyo. He is talking about a game approach to free boundary problems of an isotropic force mean curvature flow equations. Please, Takuya.
Yes, thank you very much for the kind introduction, and thank you very much for uh, uh, thank you very much to Professor Mitake and Professor Tran for the invitation to give a talk. Uh, my name is Takuya Sato from the University of Tokyo. Today, I would like to talk about some geometric PDE given by the level set method using some formulation by stationary type equations and the game interpretation for that equations. So I'd like to start from the background and the geometric models. At first, we considered some family of hypersurfaces named gamma t, which satisfies the surface evolution equation given in this form. And here, this bold-faced n is the outward normal unit normal vector field of each gamma t, and the v denotes the normal velocity along the direction to outward unit n, and this kappa means the mean curvature, which is the sum of all principal curvature at each point x on surface gamma t. And this b and c is given functions. And in this sense, the equation one means that the velocity is the velocity is given by the curvature and this outer force, and but here this curvature term is weighted in the direction n. So the some background in physics is like this one, and at first the simplest model of equation one is this mean curvature flow equations v equals to kappa. This is is given by the grain boundary movement during annealing of metals, and moreover, this kind of anisotropic model is given by the some thermodynamics of two-phase materials. And next, to analyze this kind of anisotropic post-mean curvature flow equations, uh, we use the level set method for these equations. The And here we are interested in this level set method of, for the formulation by stationary equations. This means at first we assume that each hypersurface gamma t can be represented as like this red form, which is the for some unknown function u, the each each hypersurface gamma t is written by the t level set of this unknown function u, and then we can formally calculate the value n and v and kappa by using unknown function u, and substituting n and kappa and v to the equation one, then we can get some partial differential equation for the unknown function u, like this form. Here, this du over du is equals formally is equals to n, and this term is equals to kappa times du, and yeah, and so on. at first, the viscosity solution framework for such level set equations are studied by Shang, Giga, and Goto, and Evans Black. And they are in their frameworks, they studied some evolutionary type of a level set formulation. But here we are interested in this stationary type formulation. And next, so in this study, we study this uh, a free boundary problem for the equation f equals to 1. Here, the f is this left-hand side. And we slightly generalize the model in this model and consider these four conditions for unknown function u. And this first equation corresponds to the first equation corresponds to the level set equation given in previous page, and f have this form. And the second condition is the Dirichlet condition for the boundary d0. And here this d0 is a given domain, and its boundary corresponds to the given initial surface for the surface evolution equation. And here this t is also a given parameter. And this t means an arbitrarily fixed terminal time of the surface evolution. And the rest of two conditions are called the free boundary condition for u. And this condition means that the height of u reaches to parameter t for the first time on the free boundary which is the boundary of an unknown domain dt. This is a picture for the for these equations, and here we remark that in this equation the sigma is a matrix valued function, and the c is a real valued function, and these two functions are given, and d0, the domain d0 is also given, and the t is a parameter. These four data are given data, and here this red domain dt and the blue function u are defined on unknown domain. This pair of two unknown data is called the solution for this pre-boundary problem. So in this equation, we want to know the pair of unknown data. And the main purpose of this study is to investigate some applicability for this free boundary type level set formulation. And this formulation is sometimes called arrival time formulations, corresponding to the Hamilton-Jacob equations. I will explain in the next slide about this one. And this is a usually the level set formulation is given by some evolutionary equations, but here we are studying this stationary formulation and considering the free boundary problem. So our main purpose for this free boundary problem is first to investigate the well-posedness for this equation, and moreover, we want to develop the game deterministic game interpretation for this free boundary problems, uh, and the The main result that I would like to explain today is that these two main purposes, at first we want to show the comparison principle for these free boundary problems, uh, and in the sense of this equation, the comparison principle means the ordering between the subsolution U and the supersolution V, and also the ordering between the unknown domains. And so, next, we want to construct a game interpretation, which means the some nice game which whose value function iterate whose value function approximates the solution of this free bounded problem. So, uh, yeah, second, I would like to explain some previous literature. At first, as I said in the previous slide, the free boundary problem is sometimes called the arrival time formulations. Which is this is because at first for the first order front propagation problem without curvature effects, the formulation kind of the FBP of T is called for this first order surface evolution is studied in this 1994 for Sravia's paper. And here, uh, for this equation, the level set formulation using the stationary formulation can given by this free boundary problems. Here, the Hamiltonian is given by this given alpha force C, and this Hamiltonian is one homogeneous in the second variable. And in this kind of formulations, they got some representation for the viscosity solutions for this free boundary problem by using the differential game. And yeah,
excuse me.
yes.
Can I? I'm a little bit confused. How the dynamic problem V being C leads to the stationary problem HJIT here? How
The
are they
dynamic
related?
programming is um okay, yeah, I will go to the next slide. And here
Can you, sorry, can you repeat your question, Paul? I didn't get it clearly.
Oh, I'm quite confused. It seems that Takuya showed us two problems. One is V being C, and the other is the stationary problem, which is similar to his problem. So
Right.
I'm confused. How are the two problems related?
uh
It seems that
okay.
he said they are the same
Uh-huh.
one, if I understand correctly.
Okay, so I will explain it from
Oh,
now.
sure.
And
Yeah.
yeah, and this is a first order case, and here this lemma means that the Hamiltonian given by uh, this formulation is have a minimax type formulation. So by using this formula, we can write the solution U of the equation HJI by using this inf soup type formula. And here this means the tau of x is arrival time of the differential game, which means the for given domain D0, and we are considering the equation on this domain, and this formula means that for each point x, the value u of x can be written by using the first arrival time of some trajectory determined by this ODE, and here the A and B is controls of the opposing two players, and my motivation is that sorry, at first this kind of formulation can be used in the first order case, because so but my interest is in the second order equations. So I would like to consider the applying this kind of a game framework to the second order geometric PDEs. And but in the first order case, we can use this explicit formula. But in the second order case, there are no previous works for representation to use by using the deterministic differential game. So I would like to
Can you,
consider the
Takuya? Yeah,
yes,
can you go back one slide?
yes,
Yeah, I totally agree with you because for first order case, this was done in the past, but now you can actually do it very easily that you define the maximal subsolution outside of D0. So just define the maximal subsolution of the problem in the whole R and take away D0. Then it's well defined, and then the set ut is just gonna be the maximal solution less than equals to t. That's it. So first order equation is very easy.
yeah, yes,
Yeah, but second order is a different game.
it's a yes. So and yes, for the second order case, we need to use some approximation, discrete approximation for the to get an interpretation by using the game. So this is a second previous work that I want to explain. By the Cohen and Selfati, they constructed some game interpretation for the simple mean curvature flow equations. And but here, this is not a explicit solution formula, but discrete approximation scheme for this equation, and which means there is a family of discrete valued functions u epsilon determined on omega, and this u epsilon takes step value, and this u epsilon can be determined by this so-called dynamic programming principle, and by using this u epsilon, then the half relaxed limit of this u epsilon is viscosity sub and super solution of this Dirichlet problem respectively. I'm sorry, the epsilon dropped, and this u epsilon means like this way. Here we can interpret the value of this u epsilon by using some simple discrete time game. I would like to explain this game. For each epsilon and point x, at first we let y0 equals to x, and we let some a marker at point y0, and this is a starting point. And for at for each j's turn, if the marker is at position here yj minus 1, at first the marker is on the position x. There are two players. At first, player 1 choose the unit vector vj from the unit sphere, and after seeing the player 1's choice vj, then the player 2 choose the signature plus or minus 1. And after two players' choices, and the marker moves to the next position, named yj, determined by this equation, this equality. This equality means that at first, if our marker is at point x, and then player 1 choose the unit vector. For example, the player 1 choose this vector, then and the player 2 can use plus or minus 1. This means the marker can go to the next position b or minus b, and scaled by epsilon. And then the marker goes to the next position, and we call it y1. And the two players continue this step by the discrete time, and this game this game ends when this marker reaches to the boundary of omega, and we call this step by large N for the first time. Then the player one's goal is to maximize this minimize this steps number of steps N, and player two's goal is to maximize it. And when this each player continues the rational choices, then we can interpret this value u epsilon by this public scaled steps number of steps N. And by using this arrival time for the boundary of omega, then the half-Dirac limit of this arrival time is this viscosity sub-solution and super solution of this original mean curvature flow equations. So I would like to use this kind of things to our anisotropic post mean curvature flow equations. And moreover, there are kind of previous works for by using game interpretation, deterministic game interpretation for second order equations. This is the literature I explained in the previous slide, and next Kohn and Selfati construct the more general fully nonlinear elliptic and parabolic equations. And the this number 14 and 15 is some some application of this game interpretation for the mean curvature flow. They showed some flattening phenomena for the evolutionary equations and like a convexity preserving property by using this game theoretic approximation without using no advanced PDE techniques. And the relation between the flattening phenomena in evolutionary equations and the loss of comparison principle for the stationary formulations are studied. And this 16 is about some obstacle problem for the surface evolution equations. In their studies, they showed some large time behavior of the surface by using the game interpretation. And this number 8 is about the G equation given by the convolution models, and this game interpretation are also applied to show the homogenization. Yeah, so okay, so at the end of introduction, I will summarize our aim of this study and the main results that I want to show in today's talk. Our purpose kind of like it's the ultimate goal of our study is to investigate the applicability and to fully understand the level set formulation by using this stationary equation. But today's our aim here is to establish the comparison principle, which is the uniqueness for the solution of free boundary problems. So in this context, the comparison principle means the inclusion relation for the two unknown domains and also the ordering between two unknown functions. And here, the main result is about, at first, sorry, and here the main difficulty is that we need to show the inclusion relation for the two unknown domains. So the usual PD technique, for example, the doubling value of method itself cannot work to show the inclusion relation for D and D tilde. So we need another tool. So we want to use the game interpretation for free boundary problem. So at first we give the one main result is that we give game interpretation for free boundary problem like Kohn and Selfati, and to construct some specific solutions U over bar and U under bar as a half relaxed limit of some value functions. And then by using these two specific sub and super solution, then we proved that the comparison for sub solution and super solution, but here we proved that the arbitrary sub solution have the inclusion relation to the sub-level set of this limit of value function, and the W can have the ordering between the U and the bar, and yeah, it's also for the V and D tilde. And here, by the definition of U under bar and U over bar, this under bar is equals to or less than U over bar. So from this result, we can directly know that this W is less than U under bar, and this one is less than over bar, and then this one is less than V, so which means this inequality, and the inclusion relation is also satisfied by the ordering between U bar and U bar. And here, I would like to summarize the main assumptions for our setting. Let us recall our problems. These four conditions and this blue data and this red data is unknown, and so we want to know the pair of dt and u defined on this unknown domain. And here, this function f have this form. And here, this sigma is a matrix value function, and the c is a real value function. And this c corresponds to the outer force, and this sigma corresponds to the anisotropy for the curvature. And this first condition is about homogeneity, positive homogeneity. This sigma is zero homogeneous and C is one homogeneous. And this condition can naturally given by the level set formulation. The second condition about the degeneracy of this anisotropy sigma. This means that for each p, the image of sigma p by the sense of the linear map and spans every set the subspace perpendicular to vector p. And the third condition is about the symmetry of at origin for the sigma and the c. And the fourth condition is about the Lipschitz continuity for sigma and c. And by the homogeneity condition, we can know that the regularity for the sigma and the c in the whole domain. And in the viewpoint of the geometric phenomena, the second condition means that the roof shape determined by anisotropy sigma is strictly convex. The roof shape determined by anisotropy sigma is strictly convex. And the third condition means the roof shape determined sigma and the roof shape determined c is also symmetric about origin. These two conditions, we need these two conditions by constructing the game interpretation for this equation. And by for assumption, we can easily check that the f satisfy the degenerate ellipticity conditions, and f is a geometric operator, and the f satisfies this condition about the singularity at the origin. So from these conditions, the equation f equals to 1 is quasi-linear and singular degenerate elliptic equation. And this is a definition about the viscosity solution for our equation. So we say that the pair D and W satisfying this inclusion and determine on D minus D0 is a viscosity subsolution if the function W satisfies the first two conditions in the sense of viscosity solution. And this pair satisfies the rest two conditions by in the usual sense. And we say that the dW is viscosity super solution if we change this inequality by the opposite side, and we say that the dw is a viscosity solution if sorry, there's a so both viscosity sub and the super solution, and
Takuya,
yes.
just to quickly confirm, in the previous slide, you assumed
Yeah.
that the zero boundary condition, no, the slide 12,
Yeah,
zero boundary condition is in the viscosity sense, right? That's what you assume.
Yes. This means we consider the generalized Dirichlet condition by the viscosity sense, which means
Sure, sure, sure. Sure. I just want to
in
confirm.
this
Yeah.
sense. Okay. Yeah. So here, yeah,
I'm sorry, excuse
yes.
me. And your W satisfies the elliptic equation. So you have equalities there, right? It's not
Uh,
inequality.
Sorry. Viscosity subsolution of this. Uh, uh,
So W satisfies the elliptic equation. W is not, so here it is not less or equal than 1. It is equal to 1, right?
No, is less or equals to one. Sorry. Okay. Maybe my slide is is
I
not
see.
good. So yeah. I wrote that the W is the viscosity subsolution of
Okay.
this one. So, sorry.
Got you. I see. And
Yeah,
but on
this
the
is just
boundary, as Han mentioned, it is equal to 0.
It's also
It's also
it
less.
equals or less than zero. Yeah.
Okay, I see.
Here the Dirichlet condition means this generalized Dirichlet condition, which means the sub condition for Dirichlet condition is satisfied by the usual sense, or we can extend the equation to the point on the boundary. So the first main result is we constructed the game interpretation for our equation. So for each approximation parameter epsilon, there exists some step-valued function u epsilon determined by this dynamic programming equation. And here this strategy sets D and S, and the rule of transition has delta epsilon are certain some compact set and certain function. I will explain later. And by using the half Elix limit of this u epsilon, then we can get u over bar and u under bar, which is the viscosity sub or super solution of this first two equation. And here the strategy set is like this set of vectors and a set of signatures, and we uh, uh, we fixed the transition rule delta epsilon by using this form, and here is sigma and here is c, which are given functions, and u epsilon can written by using this dynamic programming principle, and this u epsilon means this deterministic time game, which is for the abstract rule is as the same as the console parties game, but we changed the rule of transition delta epsilon to justify to adjust our equation. So for each given domain D0, there for each starting point X, the point moves by the two players' rational choices, and this radius is determined by approximation parameter epsilon. And using this game theoretic approximation, we can get this comparison principle for the original problems. So for the U under bar and its subred set, we have that if the pair dW is a viscosity subsolution of original equation satisfying this to some a kind of regularity condition for the boundary, then we have that this D this D is a larger set than the T sublevel set of this the half redox limits of value function, and on this set, this arbitrarily given subsolution is less than U under bar, and yeah, it's respectively for the super solution. For to show this comparison result, the main difficulty is that we need to compare not only the value of these two functions, but also we need to show this inclusion relationship. And moreover, we need to compare two functions in the situation such that there's no assumption for the free boundary D. Sorry, for no assumption for the ordering between W and U on the free boundary D partial DT partial D. No, this is an outline, and yes, for some arbitrarily given subsolution dW, and at first, yeah, we needed to get ordering between W and U. W is defined on this black domain, and this U under bar is defined on the Rn minus D0. Then we needed to compare these two functions without no assumption on this boundary. No assumption for the ordering on this boundary. So the strategy is that at first we take this new value function for the game Wx named by W epsilon, which is the exit time. This is the arrival time of the game from this donut shape. But in this game W, the player one can exit from the D0 side, but not only the D0 side, but also on this along this blue boundary. But here if the player one exit from this blue boundary, then the player one need to pay the more terminal cost to player two, and by using this new game W epsilon. And but U epsilon is the original game, which is to hit the D0. So, but the moving the rule about the position movement is as the same. So we can compare two discrete value function by subtracting the trajectory of the game. So using this to considering this the states of the game, we can know the ordering between U epsilon and W epsilon and take limit, we can get this ordering. And by using the usual comparison principle, we can get the ordering between subsolution and the super solution W, and we can get this ordering. Then we can get ordering between W and U. So similarly for V, we have these 5 inequalities. Then we can get the ordering between sub and super solution. And the inclusion relation can straightly satisfied by this inequality. This is a sketch of proof. Yeah, at first we defined W epsilon by using this new dynamic programming principle, which means the player one can exit from the D0 side, but the player one also exit from the boundary of D side. But if player one exit from this side, then player one need to cost large T to player two. But in the same way as main result one, we can show that this W under bar is a viscosity super solution of this Dirichlet problem under this donut shape boundary domain. And yeah, and this is a slightly technical thing, but we use this Kohl-Hopf transform for the large W, and using the geometricity of operator F, we can get this monotonicity for the equation. Then we can apply the comparison principle, and yeah, we can know that this ordering. And moreover, we to considering the nice strategy of two players that attains this inf soup, and considering that the trajectory can only through the D0 boundary, actually. We can know the ordering between this approximation sequence, and take the limit, we can get this inequality. This is a outline of proof. Yeah, yeah. Let me quickly explain the further discussion and the future work of my of this study. So the remaining task of this remaining task to know the well-posedness of this freedom boundary condition, free boundary problem, is that when the existence of the solution holds. For example, when these two Hartley-Lux limit coincides, and moreover, if the well-posedness is in some condition satisfied, then is it possible to know the large time behavior for the level sets by using this game representation? And moreover, as the previous work of Professor Liu, can we know the relation between the factoring in evolutionary formulation and the comparison principle for our pre-boundary problems? Yeah. So this is our reference list, and yes, thank you very much for listening.
Thank you, Takuya. Are there questions or comments for Takuya for his talk?
Can I ask you some questions?
Yes, please.
Thank you for a great talk, and Could you please go to page 19 or 18?
Sure.
Maybe
This one?
18. Yes, yes. Could you tell me more about how you construct the game W epsilon?
Yes, game W epsilon is um this is a given domain, and U epsilon is the hitting game for the from the starting point X to D0, and the player one can player one's goal is to hit D0, but the this blue one is the game W epsilon, and in the setting of our proof of a comparison principle, the W and the D, these two datas are arbitrarily fixed, and then we start our proof. So there is some arbitrarily fixed domain D. The game W epsilon means the player one can uh, end this game by hitting D0, or player one can also end the game by exit from D0, and player one have two choices of the uh, how to end this game. And but if player one end this game by exit from domain D0, then player one have to pay cost T to pay player one pay player one pay cost T to player two. And in this condition, no cost. Then the this W epsilon satisfy uh this dynamic programming principle.
I see. So
So
W epsilon, oh, excuse me, W epsilon and U epsilon, they are, so U epsilon does not have such penalty dynamic or penalty,
Yeah. So but yeah, U
how,
epsilon
uh,
there is no penalty for the game U epsilon, but in the setting of a game U epsilon, if the marker reach to here, but the game never ends. So
when you, it, it never ends, I see. It
yeah,
will end at time t, no? At time, or at cost capital T, no?
it no, yeah, but yes. So sorry. What do you mean?
As for U epsilon, again, uh, uh,
yeah, I
I'm not
so
very.
yeah, I mean the question Paul asks is that you consider for U epsilon you're considering the problem on Rn takes away D naught, so it's a problem on the
Mhm.
exterior domain, and then of
Yeah,
course U epsilon is getting bigger and bigger as you go further away, right? So
yeah,
effectively there's also the set D epsilon, which is where U epsilon less than T, and that's roughly speaking where you know.
yeah.
Hmm. Yeah, because the mechanisms seem quite different, so I'm just I don't quite get like intuitively how you are able to compare them.
Uh, okay. Okay. So W epsilon is roughly W epsilon is inf soup of infamized by player one, supremized by player two, and U epsilon is also Here, at first we fix the strategy of each players, but we fix the どっちだっけな。yes. So if the player one takes this strategy and from player two takes this strategy, then the this this W epsilon is less than the sorry, this is uh this infimum and uh uh sorry, how to explain? We fix the strategy SI, which attains this infimum, and second, we fix strategy SU1 and SW2, which satisfies this supremum. Then this W epsilon is less than this the SUI. Sorry. This is a value of SUI and SW2, and this is less than U epsilon. Formally, we can know this inequality, but the rule is the rule doesn't coincide in two games. So if we want to show in also in the game W, in fact the trajectory always exit from domain D0. Then we can compare the two trajectories or two strategy in these two different games. So we can uh, uh, we can we can show this inequality mathematically. So this is a really rough strategy of proof.
Thank,
Is
thank
it
you.
okay? Sorry.
Yeah, thank you.
Yeah, I think you would need to use a bit of the property of the set D, right? I mean, because to show that W epsilon
Yes.
is less than or equal to U epsilon, then
Mhm.
right, because the set D is where exactly where U is less than or equal to T, right? No. Outside of the set D,
Sorry.
U is already greater than T. That's basically why W epsilon is less than or equal to U epsilon, right? Because if you go in the way to the outside of U, then normally U epsilon would have to pay more than W epsilon. Does that make sense?
Mhm. So sorry, could you tell me once again, please?
No. I mean, your explanation is correct, but I think you should say that when you get outside the set D, then W
Mhm.
epsilon you only have to pay cos T, right? But for U epsilon, you would
Yes,
have to
yeah.
pay cos greater than equals to T.
Yes, 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 yeah, immediately is correct, but to show the U epsilon is really less than W is this is the difficult point because because basically the we cannot know the value of U on this boundary. Yes. So we needed to compare the two values to by using this trajectory, and we needed to consider these two values to uh, to go back to the domain D0.
Okay. Yeah. Okay. I think that let's thank Takuya again for a very interesting talk, and then we can discuss more informally. Okay. Thank you, Takuya.
Thank you very
Thank you.
much.